All right, everybody. Good to see everyone here today. Let's get the lecture going for this afternoon. So this afternoon, we're going to be continuing thinking about thermal physics and thermal energy. And we're really going to be focusing on the relationship between heat energy and temperature. So in the last lecture, we got introduced to kind of some of these concepts, the idea of heat as a form of energy. And we also saw the idea, we have this Kelvin scale when we're thinking about temperature in physics, because that corresponds to a scale of 0 when we have molecules which aren't vibrating. So what we're going to be thinking about today is if we want to change the temperature of something, or if we want to change, as we say, the phase of something, so maybe melt something or boil something, how much energy do we have to do to achieve that? So that's the plan for today. Now, I've just got a couple of pictures that I'd like to show you guys to give you guys a kind of couple of extreme examples of what can happen when we're thinking about the ranges of temperatures and the ranges of energies that we think about in the solar system. Okay, so I've got this picture over here. This isn't actually a photograph, even though it looks very realistic. This was actually reconstructed from radar data by a European Space Agency mission orbiting Mars. This is the Korolev Crater there, and this fantastic white snowy sort of thing, it really is just frozen water ice. So we know on Mars there's lots of frozen ice caps, and then we've got all this ice in this crater. Now the temperature on Mars, it's 208 Kelvin, and that might sound nice and toasty warm, 208. Maybe you could bake something at that kind of temperature, but remember how Kelvin are related to Celsius. So in Celsius, it's minus 65 degrees Celsius. So pretty chilly, okay? If you're ever going to be a Martian astronaut, you're going to want to make sure you keep yourself nice and warm there. So that's Mars. Just for a bit of contrast, let's take a look at Venus. So I've got this photo here. This is a panorama photo assembled from several individual photos of one of the very few probes by the Russian Space Agency to make it all the way down to the surface of Venus. And these probes don't last very long at all when they reach the surface, because Venus is extraordinarily hostile. So the temperature on Venus, 730 something Kelvin, which in Celsius, so 464 degrees Celsius. So it really is, you might fairly say, like an oven. It is really hot planet. It's hot enough to melt lead, and in fact it rains sulfuric acid there. So a couple of extreme examples from our very nearest planetary neighbors. And with both of these planets, whether we're looking at extremely high temperatures or low temperatures, what causes this is the amount of energy that the planets receive in each case. And if you want to be somewhere like Earth in the nice Goldilocks zone where we have lots of liquid water and agreeable temperatures for that, then you've got to have that balance of energy just right. So those are some of the things we're going to be finding out a bit more about today. Now, before we start with some questions and start thinking a bit more about heat energy, I'd just like to start by thinking about a couple of sort of observations, a couple of facts that we can start to string together whenever we're thinking about how to relate temperature to heat energy. So one of the first things I'd like to start with, it's just this observation that if we have some heat energy over here, that's going to be proportional to our change in temperature. So proportional to our delta T. Has anybody seen this proportional symbol before? How many people have seen the proportional notation before? Okay, so if you haven't seen the proportional notation before, that's absolutely fine. All it means is that these two concepts are related, but they're not directly equal. So you can kind of think about this as a relationship. So suppose we've got our temperature over here. If we wanted double the change in temperature, then we're going to need twice as much energy. That's kind of how proportionality works there. So the other thing which we can kind of take as a sort of experimental starting fact to relate energy is that the heat energy we need to change temperature also depends on how much mass we have. So we can also say, you know, our heat energy, it's proportional to how much mass. And hopefully this one might be fairly intuitive as well. So if we have, you know, a kilogram of something and we want to change the temperature, and then we think about how much energy we need, well, if we had twice as much, then we're going to need twice as much energy. So both of these things, the mass and the change in temperature, we say they're both directly proportional to the heat energy required to do that. So we can kind of take these two things as sort of starting facts to start to piece together the puzzle of how much heat energy we need. So let's start with this question over here. If we start with these two observations here, that our heat energy is proportional to our change in temperature and it's proportional to our mass, how can we put these together in an equation, not just a proportional relationship, that's going to tell us how much energy we need to change a certain mass by a certain temperature? I'll just get the question going. Let's see what everybody thinks for this one. So if you're not sure about this one, just look for the equation where the heat energy, it's directly related to the mass that we need and the change in temperature. That should help you pin down which of those equations is the right one. Okay, let's take a look at the responses. Let's see what everybody thinks for our heat energy over here. What have we got? Oh, okay, so nobody's going for A. Some people going for B, some people going for C, some people going for D. Now, I thought with option D, you might be tempted for that one because we've got that mc squared there, okay, and that looks a bit like a kind of familiar equation that might be very famous in physics. But in this situation, this little c, it doesn't represent the speed of light. It represents what we call the heat capacity of whatever we're thinking about. And you can think of that heat capacity, it's really what determines this proportionality here. In kind of math terms, you might say it's the constant of proportionality. So we don't need to square it there, even though that c squared, that mc squared might look like it's kind of that energy that we like from E equals mc squared. But option D, it is directly proportional to temperature and mass. So it does have that part of the equation that we like, but we just don't need to be squaring that constant of proportionality there. So if we're thinking about B, so that does directly depend on our mass. So if we double our mass, if we triple our mass, we're going to need twice or 3 times as much energy. So it does have that dependence on mass that we like. But if we look at the equation there, we're dividing by delta T. So what that would tell us is that the more we wanted to change the energy of something, the more we want to change the temperature of something, the less energy we're going to need, which is kind of the inverse of how it works in practice. So the correct option, the one which is directly proportional to mass and our change in temperature, is option C there. So very well done, everybody who gave that question a go. Now, there's a couple of things that I'd like to emphasize about this. So the first of all is that this is a very important equation whenever we're thinking about thermal physics and thermal energy. So definitely one to write down in your notes, maybe put a big old box around it or something like that, because it's a very important relationship. The other thing I'd like to kind of suggest and consider with these equations is I'd really want to emphasize, don't memorize any of these equations, and let's try not to see them as just arbitrary things, because certainly by the time you get to the end of a semester of taking physics, you might end up with a lot of equations and a lot of different relationships, and it might not be intuitive to see where they all come from, and they might seem a bit arbitrary. So the thing I want to emphasize with this equation is that nothing there is arbitrary. All this is telling us in the form of an equation is that heat energy is directly proportional to temperature and mass, and that proportionality is something that we call the heat capacity. So that's the basic idea with that. So very well done, everybody who pins down that equation, because you're really starting to think like a physicist if you can spot that one. Let's think about this specific heat capacity a bit more. Let's think what the units of this proportionality are going to be. So we know that our heat energy, it's mc delta T. I'm sure by the end of a few lectures of this, you'll never be able to forget it. It just kind of sticks in your head like that. But let's think what units we need to have for this heat capacity so that our change in mass and our change in temperature is going to give us some energy. So you really don't need to guess with this question at all, because remember, we want the equation to come out as a form of energy, and it depends on mass and it depends on temperature. So that really does completely pin down what we have to have for the units of our heat capacity there. Okay, let's see what everybody thinks for the units of our heat capacity. What do we have here? Okay, so nobody's going for C, some people going for A, B, and D. So if we look at the equation up there, we want something to have joules in there. So we know that the starting sort of unit for our heat capacity, it's got to have joules in there, which they all have. But then we're multiplying it by mass, that m there, and we don't want our heat energy to have any mass in there. So we need to be dividing out by kilograms there. So we're looking at maybe A or C. And then also we've got that delta T there, which has got units of kelvins, and we don't want any temperatures showing up in our heat energy. So we need to divide that one out as well. So when we do that, well, we end up with option C there for our heat capacity of a material. So very well done if you got that one, if you gave this question a go. And I'll just repeat with this one that you don't need to guess with these kinds of questions. By looking at what goes in, we can figure out what has to come out from this. And thinking about units, it really does help when we're thinking about problem solving. The last thing I'll say about heat capacity on this slide is that it varies depending on material. So some materials, they take more energy to change the temperature. And within a material, it changes depending on whether it's a solid or a liquid or a gas. So if we look at the heat capacity of something when it's in liquid form, that's not going to be the same capacity as when it's a solid or when it's a gas. So just something to watch out for there. Let's try an example of this with a specific calculation, see how it kind of works in practice a bit. So suppose we've got a bar of aluminium, and we're thinking about, okay, maybe we've got a kilojoule of heat energy. So how much could we change the temperature of our bar of aluminium with our kilojoule of energy? And this is kind of, we can see how the heat capacity works a bit there. So we know that our heat capacity for solid aluminium, so it's 921 joules per kilogram per Kelvin. So let's see what everybody gets for this. How much can we change the temperature of this bar of aluminium? So with this one, we have to do a bit of rearranging, do a bit of algebra before we're ready to crunch the numbers. So I'd always suggest when we have an equation like this, do the rearranging first, solve for that delta T before putting any numbers in and before reaching for your calculator. That's going to make it much easier to work out what the actual value is when you come to doing the calculation. Okay, let's see what everybody thinks. How much can we change the temperature of this bar of aluminium? Let's have a look. What have we got? Okay, so looks like most people going for option B there. So let's just work through the algebra just a little bit in case people aren't too sure. So remember, we've got our heat energy. So Q is equal to mc delta T. And we're thinking about what's our delta T going to be given Q, M, and C. So let's do the algebra first. Let's do the rearranging. So we're going to get our delta T is equal to Q divided by MC. So I'd always just do the rearranging first before putting any numbers into your calculator. Makes it much less likely that you're going to make any mistakes with your calculation. So when you do that, when you put the values in, we get our delta T. It's going to be that option B there, so 2.4 Kelvin. So very well done, everybody who gave that question a go. So hopefully, if we're just thinking about changing the temperature of something, looking at how much energy we need, we've got this direct relationship. So I'd like to try a slightly more interesting question now, where we're not just looking at the energy involved, but we're also looking at the power. Now, very often in physics, we might be thinking about very esoteric situations. We might be thinking about, the temperature on Mars or Venus or the power output of the sun or something like that. But I'd like to take a very down-to-earth, everyday example to think about for this one. So let's think about boiling a kettle. Maybe we want to make ourselves a cup of tea or something like that. So suppose we've got a 1.5 kilowatt kettle. So remember, that means that every second our kettle is drawing 1,500 joules of energy. And we want to boil a certain amount of water. Now, we know the initial temperature and we know the final temperature because it's going to be boiling. So we can work out how long is it going to take to boil the kettle. Now, for this one, because it's water, not aluminium, we need to use the specific heat capacity of water. So 4,186 joules per kilogram per Kelvin. Who's seen the specific heat capacity of water before? Oh, okay, not too many people. So if you remember, do you guys remember calories? We looked at calories as a unit of energy last time. So a calorie is all to do with how much energy we need to change the temperature of water, if you have seen that value before. But that's the specific heat capacity that we need for liquid water. So let's see how everybody gets on with this one. So there's a few steps to this one. It's up to you to work out which way might work best for you if you're solving this one. So we need to think about how much energy we're going to need, and then we need to think about how much time we want to work it out. If you like, you can work those out separately, or you can combine the equations a bit, put them together, and see what you get for that. Okay, let's see what everybody gets for this one. How long is it going to take to boil our kettle? What's everybody get here? Okay, so we've got some people going for all the options here. How many people works out the total energy you needed first? How many people figured it out that way? Okay, and how many people put the equations together, rearranged, got time, and then put all the numbers in? How many people did that way? Okay, very good. Did anybody else solve it any other ways? Or were those the two main ways? So with this one, either way is fine. Sometimes it is useful to see, what the total amount of energy is you need. So when you put the values in, we get a time in seconds. We just got to be a bit careful when we convert that time into minutes and seconds. And what we get is the 2 minutes and the 9 seconds there. So very well done, everybody, with this one, because it's quite a tricky question. So really pleased to see everybody working out those values are right there. That's really good. So that's the situation if we're changing the temperature of something by putting in some energy, but we're not thinking about, we're taking our kettle all the way to the boil, but we're not thinking about boiling the kettle. Or similarly, maybe, sometimes you might have some ice, you want to defrost the ice. How much energy are we going to need for that? So we've got to think a bit more about the energy involved with that. And there's a very useful kind of diagram, a way to think about all of this, the energy we need to change between different states of matter. So let's take a look at the diagram. Let's see what we get for this. So what we've got on this diagram, on this axis over here, the horizontal axis, we've got the heat energy that we're putting into something. And in this example, we're thinking about good old-fashioned H2O, okay? So the good old-fashioned water that we're also familiar with. The basic principles apply for anything, but I think it just makes sense to take a look at how this works for water. So on this axis, we've got energy. If you look at the units for energy, it's given in terms of calories per gram. So maybe we might be more familiar with, joules per kilogram in terms of the energy that's going in per mass. But remember, calorie, it's just another unit of energy. And for water especially, it's a sensible unit to think about when we're looking at energy. And then over here on the vertical axis, we've got temperature. And just so it's kind of a bit more familiar, we've got that temperature scale in degrees Celsius. So especially for water, you know, Celsius was really the temperature scale designed especially for water. So we've got very natural points for the boiling and freezing points of water. So if we have a start over here, we've got some ice. If we add energy to it, we raise the temperature of the ice until it reaches 0 degrees Celsius. And then what happens if we look at this next part of the diagram over here? If we keep on adding energy, we don't raise the temperature of the ice. Instead, what we do is we melt the ice. So that energy that we put into the system, it's actually doing work on the molecules of the ice to turn them from ice into water. So pulling those molecules apart, that takes work. So remember, work, in a sense, it's the most fundamental form of energy. Heat is just another form of energy. So we really have energy going in as heat, and then it's being turned into work. So once we've melted all our ice and it's turned into water, we've got the situation we were just looking at with the boiling kettle here. So we've got this line here, and the more heat energy we add to our water, the more the temperature increases. And then as we get over here to the other part of the diagram, once we get to 100 degrees Celsius, we can't raise the temperature of the water anymore and still have it being a liquid because it's going to start to boil. And again, it's the same kind of idea as with the ice cube. So we're adding energy. We are still adding energy to the system. But if you look, the line is horizontal. Okay, so we're not raising the temperature. Again, that energy is going into boiling the water. And then the last part of the diagram, once we get to steam, we're back to this situation where we can add energy and we are increasing the temperature. So the couple of kind of things we need to know to figure our way around a diagram like this. So whenever we're on a sloping part of the diagram, our change in temperature, it's given by this relationship that we've seen before a couple of times now. So Q is equal to MC delta T. Once we get to these flat parts of the diagram, the amount of heat we put in, it's not affecting the temperature. So what we have over here is that the energy that we put into the system, so whether you're melting something in a microwave or something like that, it just depends on the mass, and then we have a little L there. And that little L there, it's still the same kind of idea, it's still kind of heat capacity. It tells us how much stuff we can melt depending on how much energy we put in, but it's a very different value to that heat capacity, to that C over there. Just to kind of spell this out, the C and the L, they're not only different for different materials. So if you're looking at, maybe a metal, you're looking at iron or something like that, or you're looking at water, they're going to have very different values. So the change in temperature that you get, given the amount of energy, it's going to vary depending on what the material is. But also, it depends on what state that matter is in, whether it's a solid or a liquid or a gas. So that heat capacity we have for water, if we were thinking about increasing the temperature of ice or increasing the temperature of steam, we have to use the appropriate heat capacity. You can't use the same heat capacity of water. There's also this different heat capacity between how much energy it takes to melt something versus how much energy it takes to boil something. So when we're boiling, that's called the latent heat of vaporization. So that L there, the heat of vaporization. And I think that's a kind of sensible name. How much energy do we need to vaporize something? That's what we're doing when we're thinking about boiling something. The slightly less well-named thing over here, the L that we need to melt something, it's called the latent heat of fusion. I think it would be much better, much more straightforward if this was called, the latent heat of melting, because that's exactly what's going on. So just to kind of point out with this, that this latent heat of fusion, it has nothing to do with nuclear fusion, okay? if you have some water and you're undergoing nuclear fusion, you're at much, much higher temperatures than if you're just thinking about melting some ice. So it's kind of the name we're stuck with, the latent heat of fusion. The idea with calling it fusion is if you have something which is solid, which is ice, when you melt it, everything's going to fuse together when it turns to a liquid. But it means fusion in terms of mixing together, not nuclear fusion. So that's just the name that we have for that. So if we're just thinking about water, there's actually kind of 5 different values that we need to bear in mind to describe everything that goes on from turning some water from ice all the way into steam. So we need to know what the heat capacity is when it's ice. We then need to know the latent heat of fusion, so how much mass we can turn into water for the energy that we put into it. Then back to that familiar situation with water that we've seen, and then the same kind of idea over here where we're looking at boiling some steam. So we're turning the water into steam without raising the temperature. Once it's steam and we keep on putting energy, then we raise the temperature over there. So that's the basic idea. We've looked at this example for water. Most things that we might be considering, even if it's something like, a metal, obviously we don't kind of on the day-to-day basis think of metals as, frozen, or, we don't want to be thinking about boiling off metals, but it's the same basic idea that if you have a solid metal and you heat it up, it's going to melt, turn into a liquid, and if you keep heating it up even more, then it's going to undergo a different phase transition as well. So let's try a quick example question, see how this is going to work for water here. So suppose we've got a little ice cube here, and we want to think how much energy is it going to take to melt our ice cube here. So you'll notice this value here, this L, 334 joules per gram, is very different to the heat capacity of liquid water. So we just got to bear that in mind when we're thinking about this. So I'll get the question going. Let's see what everybody thinks for this one. So with this one, we don't even need to rearrange this equation at all. We're thinking about the energy required, we've got the mass, and we've got the heat capacity. Okay, very good. Good to see all those responses coming in. Let's see how much energy we're going to need to melt this ice cube over here. Oh, okay, fantastic. 100%. I've probably given away that this is the correct answer as well, which it is, okay. So that's absolutely fantastic. It's great to see everybody getting this one the correct answer, okay. So very well done, everybody who gave this one a go. What does everybody think of this energy to melt an ice cube? Any thoughts about that? So nearly 10,000 joules of energy just to melt an ice cube, okay? So quite often, whenever we're thinking about the energy involved to melt something, vaporize something, even to change the temperature, we end up with a lot of energy, okay? It takes a lot of energy to change the temperature of water. So that's with ice. If we apply a lot of heat to it, it's going to melt. Does anybody know what happens to solids before they get to the melting temperature, especially when we're thinking about metals? Anybody know what happens with this? Any thoughts? Where are all the engineers? Who's focusing on engineering in here? Okay, now with the engineers, is anybody interested in mechanical or aerospace engineering in particular? Oh, okay. Which ones that you're thinking about? Mechanical, okay. Any other mechanical engineers? Okay, and anyone who kind of likes the idea of aerospace engineering? Okay, so even if you're not interested in aerospace engineering, this is a very important concept, really for everybody, but especially for the engineers, because you might sit down and design, a nice car or something. You might design a ship or something, but once the thing starts moving, once it starts heating up, everything's going to change shape a bit, because the heat energy that we put in before we get to melting something, we actually get this phenomenon called thermal expansion. And I think one of my favorite examples of this is the SR-71 Blackbird over here. Has anybody heard of this story before? Oh, yeah. So the SR-71 Blackbird are one of the very fastest aircraft ever made. And as it was traveling at such high speeds, punching through the atmosphere, the whole aircraft really heated up by a huge amount. And that caused the whole aircraft to change shape, okay? So to account for this, the engineers actually had to leave gaps in the fuel tank. So when they filled up the aircraft on the ground, it just leaked out fuel, and it actually took off leaking off fuel. And you can see that this photo was actually taken from an in-flight refueling tanker. So the first thing the SR-71 has to do once it's taken off has to get refueled. And once it's flying along and the whole aircraft has warmed up a bit, those gaps in the tank close up and it doesn't leak all over the place. But it actually causes the aircraft to stretch due to this thermal expansion. So the last couple of slides I'd like to think about today are just focusing on thermal expansion and how much something is going to expand based on how much temperature change we're thinking about. So the situation we have for thermal expansion, as an equation, it looks quite similar to some of the other relationships that we've seen today. So what we have is, if we have something which is a particular length, so the length of a stick or the length of an aircraft or something like this, or maybe if you're an engineer, this could be the length of a bridge, something like that. The change in the length, again, it's directly proportional to the change in the temperature. So it's another proportional relationship. And when we're thinking about thermal expansion, that constant of proportionality, it's called that alpha there. And again, it depends on the material. So let's try with this question. What are the units that we're going to need for that coefficient of thermal expansion? So again, with this one, you don't need to guess at all, even if you haven't ever seen thermal expansion before, because we know that we're trying to calculate a change in length. And we know that's going to depend on the original length and what our change in temperature is. So based on that, we can figure out exactly what the units of that coefficient alpha have to be to make this equation work. Okay, let's see what everybody gets for this one. What are the units of our coefficients here? Okay, so a bit more spaced out over here. Now I think the key to this one is thinking about the units that we're going to end up with. So if we have a look over on this side, so that delta L, that's a length, so how much our length has changed. And that's going to have the same units as our initial length there over there. They're both lengths. So whether we're measuring that length in meters or inches or feet, we've got those units on both sides of the equation. It's just on this side of the equation over here, we only want to have the units of length. So remember that delta, it's a change in something, but it's going to have the same units as the length that we started with. So then if we look at the other side of the equation, we've got a temperature over there. So that delta T, that's going to have units of Kelvin. And we don't want that showing up when we're thinking about our change in length there. So to get rid of that, our coefficient, it's got to have units of per Kelvin. So that's option B there. Okay, so very well done, everybody who gave this question a go. If you're not too sure about this, this is a great kind of question we can go through at the workshop, just to work through all of the algebra with that, okay? So the last question for today, let's think about that example of the SR-71 Blackbird. So we know that the Blackbird is 33 meters long. That's our initial length. And when the Blackbird's flying, the pilots reported that the aircraft would stretch out by several inches, so about, let's say, 8.9 centimeters. Now the Blackbird, it really heated up a lot because it's flying many times faster than the speed of sound. So we know our delta T there, our change in temperature, so about 317 Kelvin. So Remember, that's the same change in temperature as 317 Celsius. So the aircraft really did heat up a lot there. So let's use these values. Let's see what we get for the coefficient of thermal expansion for our Blackbird. So with this one, just watch out for the units, because remember, the length of the plane is measured in meters, and the length of our change is measured in centimeters. So we just need to be consistent with that. So if you like, you can convert the length of the plane into centimeters, or if you prefer, you can convert that centimeters there into meters. It's up to you which one you do. Remember, the important thing is just to be consistent. Okay, so last question for today. Let's see what everybody gets for this one. What do we get? Okay, so nobody's going for B. Looks like most people are going for D. Did anybody convert the length of the plane into centimeters? Did everybody convert it to meters? Did everybody? Okay, that's absolutely fine. Just as long as you're consistent with that. Otherwise, you'll be off by a factor of 100. So when you do that, you put the values in. We get an alpha of this 8.5 times 10 to the minus 6. So very well done, everybody who did that. Okay, and especially if you look at the units there, they're units of per Kelvin. And based on what this coefficient of expansion is, we can have a clue at what the aircraft is made out of. Did you guys look up get the value okay?
Yeah, it's 7.14 times 10 to the minus 6 or something.
Okay, so pretty close, okay? So this is actually the thermal coefficient of expansion of titanium, which is what the aircraft is made out of. The aircraft is basically titanium. So that's what's going to determine how much the aircraft is going to expand by. One last thing to say about this. If we look at how much the aircraft is going to increase in temperature by, that really does determine the kind of materials that we can make the aircraft out of. So titanium is very expensive, it's very difficult to work with. But if your aircraft is going to heat up by this much, it's no good making it out of aluminium or something like that, because your whole aircraft might melt, and that would be very bad news for everybody. So based on how your aircraft's going to perform. You got a question there?
I actually got it wrong and read it wrong. It's 8.5.
Oh, okay, it's exactly 8.5. Okay, thank you for the clarification about that. Exactly 8.5. The one thing with exactly what the value is, it might depend a bit on what the exact alloy of titanium is, and also exactly things like the pressure and exactly what the temperature is. So if it's a bit different, that's fine. But if it came out exactly 8.5, that's great. Okay. So that's the last question for today. Very well done with all those questions today. Just a reminder, we've got the workshop tomorrow. Now, the challenge question in the workshop is an absolute all-time classic physics question. And I'm sure everybody would be able to manage it. We've covered everything that you need to give this challenge question a go. So if you haven't done the challenge question before, do think about giving the challenge question a go tomorrow. One last announcement about the workshops tomorrow. I'm going to be telling everybody about the coursework in the workshop tomorrow. So the coursework is kicking off this week. Make sure you come along to the workshop. I'm going to tell everybody all about it, okay? So excellent work today, everyone, and I'll see you all tomorrow.